welcome back to mass transfer operations 2 course, and we were discussing on adsorption and ion exchange. In the last class we discussed on stage wise and continuous adsorption operations. Now we will be discussing on fluidized bed and teeter bed and steady state moving bed adsorber. So, in the beginning we need to learn about the different fluidized beds in the application of the adsorption processes, and nowadays the use of this fluidized bed for the adsorption purpose is increasing gradually, and so these are used to recover vapor from this vapor gas mixture, to fractionate these light hydrocarbon vapor with the carbon, and say we need to consider a bed of granular solids up through which a gas flows from the bottom, and at low gas rates this gas suffers pressure drop, which can be estimated by this Argan equation like this Argan equation for this pressure drop across this length L, that is equal to say 150 this VO bar and mu into 1 minus epsilon square divided by phi s square into dp square into epsilon cube plus 1.75 into rho into VO bar square into 1 minus epsilon divided by phi s into dp into epsilon cube. Okay, so, where we can say this delta p is the pressure drop across this we can say the column, and L is this length of the column, then we can say this mu, that is we can say viscosity in we can say Cp in centipoise, then epsilon is equal to we can say this porosity, and we can say this phi s we can say sphericity of the particle, then dp will be say diameter of the sphere, and rho is this density, that will be kg per meter cube. Then we can say L, actually we can say the length of this fluidized bed, and VO bar, that is we can say this superficial or empty our velocity, that is we can say this meter per second. Okay. So, this using this Argan equation we can estimate the pressure drop across the we can say this column, and at the incipient of fluidization. So, we can see this at incipient fluidization. See delta p by L, that will be like g into 1 minus epsilon m into rho p minus rho. Okay, this where this g actually we can say this gravitational constant, that is gravitational acceleration, so meter per second square, and this epsilon, that is we can say this that is the voidity, or we can say that is the porosity, and rho p, that is the density of the particle, whereas rho is the density of this what is called flowing gas. So, we can say this one at minimum fluidization velocity, that is we can say this one VOM bar, we can say this delta P, that will be like this weight of this bed divided by this unit area of bed, allowing for buoyant force. Okay. Then we can say whatever the Argand equation we have, the first part, that is we can say when this particle Reynolds number is less than or equal to 1, we can say that time this we can say Koizeny-Karman equation will be this one valid, and when this we can say particles Reynolds number is greater than equal to we can say 1, especially this greater than 1, we can say this Burke-Plummer equation. This will be valid. So, whenever we have these particles Reynolds number ranging from very low Reynolds number to the higher Reynolds number, so we have this we can say this combined form, like we can say whatever the first part is 150 VOM bar into mu into 1 minus epsilon m whole square divided by this phi s square into dp square into epsilon m cube, that is we can say this part we can say for Koizeny-Karman, and 1.75 into rho into VOM bar square into 1 minus epsilon divided by phi s into dp into epsilon m cube, that will be equal to we can say that is del p by L, that will be equal to we can say this one G into 1 minus epsilon m into rho p minus rho. Okay. So, that this part we can say this one Burke-Plummer, this equation we can say where we can say this Re particle, that is we can say is greater than 1, where this part is we can say this one Re particle less than equal to 1. So, in that case we can say so this using this equation we will be able to get the we can say this what is the minimum fluidization velocity for a particular material having this diameter width of the particle at dp and the we can say voidity as epsilon m. Okay. So, that we can get this one. Suppose for small particles only we have suppose small particles, and we can say this one where Reynolds number particle is we can say less than equal to 1, then VOM bar that will be equal to, so from this equation we can say this one G into rho p minus rho into epsilon m cube into phi s square into dp square, so divided by 150 into mu into 1 minus epsilon m. Okay. So, that is we can say this one if we do the manipulation, or we can say this one the second part of the left hand side of this equation that is will be vanished. So, then we can say for small particles like this, whenever we can say this if this particles Reynolds number is we can say this one very high, let us take say for greater than 1000 like this, then we have this, we can say this, in that case this minimum fluidization velocity will be equal to, say this only second part will be there, first part will be vanished. So, by manipulation we will be getting that VOM is equal to phi s into dP into G into rho p minus rho into epsilon m cube divided by 1.75 into rho this whole to the power 1 by 2. So, in that case we can say this minimum fluidization velocity will be this. Okay. So, that way we will be getting the minimum fluidization velocity for different cases whenever we will be doing the adsorption process using the fluidized bed. Okay. So, then as we can say this velocity increases, so then pressure drop actually equals this weight of the solid plus friction of the solid with the wall. So, if gas velocity is further increased, then solid bed will be enlarged and then void edge will be increased, and then we say this one as quiescent fluidized bed. Means the entire bed will be enlarged, and then we can say that is just before the fluidization like this of the entire solid material. Further increase in the velocity makes the bed like a boiling liquid. So, it will be like, so the entire thing will be boiled, like the solids will be like boiling, because we are applying this gas from the bottom, and then suppose solids are placed here, and then it will be like boiling like this. So, this condition is used for the adsorption, and in this case the adsorption will be maximum. So, solids are carried away with the gas. So, that then this one scientist A. M. Squares has distinguished between this fluidized bed and teeter bed. So, these are almost similar, only the small differences are there among these two beds. Like with this fluidized bed, we can say the particle sizes are, we can say this 20 mesh to 350 mesh screen. So, and for teeter bed actually we can see these coarse particles will be there more, say less than 10 mesh screen, these one materials actually are there. So, with big size materials. Then for fluidized bed, superficial velocity will be, we can say very small, like this 0.6 meter per second like this, and 10 times this we can say the minimum fluidization velocity. And for teeter bed, as the particle sizes are very coarse, we can say this one 2 times this we can say this fluidization velocity is minimum required. So, that is we can say this one ranges from 1.5 to 3 meter per second. Okay. And say we can say this in case of the fluidized bed, as this is very this is the operation related to the finer particles. So, we can say lesser fluid solid contacting is there in case of the fluidized bed, but for teeter bed the better fluid solid contacting is possible, because the solid coarse particles are very heavy, and say we can say this one, and it moves very slowly. That is why we can say the adsorption of the target component takes place very we can say systematically, or we can say this one in a very good manner. And solids are means solid particles are fluidized by the gas only. Here solids are fluidized by both gas and the solids. Okay. So, there we can see this one small differences are there. Now, we will be discussing about the solid state moving bed adsorber. This is we can say the like this Higgins contactor. This is very good in we can say this on adsorbing this target components very efficiently using the solid materials and followed by regeneration, and it is done steadily, or we can say this one as till now whatever we have discussed there, say we have the adsorbent, and adsorbents are sticked on the top of the adsorbent sides, and once the adsorption process is over, then we can say this all the adsorbents will be this one regenerated to use in the next adsorption process. But in this case we can say we will be able to use the same adsorbents very efficiently for a continuous operation using the same adsorbent. So, somewhere it will be adsorbed, and at the same time other part will be regenerated. So, like this if we say this is the contacting part. So, we can say suppose the adsorbents are placed here and we are feeding this feed from this top like this. Then in this zone say suppose adsorption is taking place, then this valve will remain closed and the bottom part actually we can see this one, this is regeneration zone. So, here say suppose this this valve actually we can say here also will remain closed. So, this one pulse section will be there, that will be used to we can say we can say this to the adsorption process to be held here. So, what is happening say in the beginning, suppose in the first stage this adsorption process is going on and at the same time whatever the adsorbed this one what is called solutes or adsorbents were there or exhausted adsorbents were there, these are now placed in this section. Just by say if we just pressurize the system, then whatever the adsorbed material will be coming, what is it came actually from the previous we can say operation. Whenever it will be entering, then say some regenerants are added there along with some rinse water, and this overflow is actually used to separate the we can say target component or adsorbate. So, through overflow we can say adsorbate actually is separated during this regeneration process. So, the regeneration process is like this temperature swing or concentration swing, that will be discussing in the next class. And say, but you see in the beginning say using the suppose this pulse, suppose this for the say adsorbate actually is entering here and adsorbent is loaded here, this fresh adsorbent. So, whenever we have this adsorption process, then regeneration process will be going on parallelly. So, once the we can say it is entirely exhausted, then we need to open this valve and we need to open these two valves. Then what will be happening, say the whatever the adsorbed solids or we can say this here say this adsorbent and adsorbate. So, this both this will be taken to here just by opening this valve, and the total adsorbate and adsorbent will be coming here, and that time this we can say this one fresh adsorbent actually whatever was generated in the previous section previous operation will be coming and filling this we can say the we can say contacting chamber. Okay, so, that way using this Higgins contactor the adsorption process is made continuous, though these are of we can say batch type or semi batch type, but the process will be going on in this way. So, firstly in this contacting chamber with the fresh adsorbate will be added, and at the same time in the regeneration chamber whatever the adsorbate and adsorbent were there, these will be regenerated, means this through the overflow adsorbate will be separated. So, fresh adsorbent will be coming. So, in the next operation this fresh adsorbent actually will be dosing to this contacting chamber, and at the same time whatever exhausted this adsorbent and adsorbate will be there, that will come to regeneration chamber. So, this is the we can say cyclic process. At the same time we can say the fresh adsorbents will be coming and it will be attached, it will be this one adsorbing the adsorbate. So, this if we do the mass balance actually in this bed like this suppose this is the adsorbent bed, like this we can say like whatever we have done in case of this humidification operation. Let us take suppose this gas is entering with this flow rate of say G with this concentration of the target component of Y1, and say we can say it will be leaving this chamber like this with G or GS, whatever we can say this one. If we say this one GS, then it is we can say this GS with we can say Y2. This is station 1, this is station 2, and whatever the we can say this adsorbate actually that is entering, say we can say this an SS with we can say the concentration of X2. Whenever it will be leaving the chamber, then we can say this one dry wet flow rate is SS with this solute concentration of x1. Let us take one we can say this one differential thickness of say dz, because we assume that this z direction will be say from point 1 to point 2 like this. So, dz will be there, say through this we can say the both this liquid flow rate and gas flow rate will be, or we can say this one adsorbate flow rate and the whatever the we can say this one adsorbent flow rate will be there. Suppose this is taking place here and we will be doing the simple mass balance. Okay. And there we can say this, if this is say we can say y plus dy, then it will be like y, and if it is x, then it will be x plus say dx, or the concentration of the target component in both the streams. Like then we can say if we do the solute balance. So, across this tower, then it will be solute balance. So, then will be G s into say y 1 minus y 2, that will be equal to S s into x 1 minus x 2, and say we can say this rate of solute transfer over this differential height dz will be like this, S s into dx is equal to G s into dy will be equal to k y a into y minus y star into dz. Okay. So, where this k y a we know this one overall mass transfer coefficient actually based on this outside surface area, we have already discussed this one previously, and then we can say this NTOG and HTOG, that also we have derived, that is y 2 to y 1 will be having this dy by from here actually this one from this equation y minus y star, that will be equal to k y a, say that is we can say this constant parameter by G s also, that is as this is we can say this solute free basis. So, that will be also constant. So, we can say 0 to z means from bottom to top, that will be we can say this one dz. Okay. So, it will be nothing but we can say this NTOG will be nothing but that will be is equal to z by this HTOG, where this that will be dz, and where HTOG will be we can say this HTOG, that will be equal to G s by k y a. Okay. So, this is HTOG and NTOG will be like this, NTOG will be coming from this expression. Okay. So, from there if we just multiply this NTOG and HTOG, then we will be getting Z, because Z is equal to the multiplication of NTOG and HTOG. Okay. So, from these two we can say we will be getting, if we know NTOG and HTOG, then we will be getting what is the height of this adsorber column. Okay. So, now we will be this one solving a small problem from this Langmuir isotherm, like this adsorption of pure gas A on activated carbon follows the isotherm Q is equal to 6.4 P by 1 plus 1.53 P. So, like this Q is equal to Q m into K p by 1 plus K p. Okay. For this P is in kilo Pascal and Q this is that is in millimole per gram. If the molecular weight of A is 65, what is the maximum quantity of gas that can be adsorbed in kg adsorbate per kg carbon? Like this, whatever this what is called you say millimole per gram from where if we just multiply this one with this molecular weight, we will be getting suppose gram per gram, that will be equal to kg per kg. Okay. So we need to understand that, say we are trying to get the maximum quantity of gas to be absorbed on the activated carbon. So, we will be starting with like this. We know that as per this Langmuir isotherm, Q is equal to Q m into K p by 1 plus K p. But at the same time, if we say this, if we want more solute to be this one adsorbed, then if we want to make Q is equal to Q m, then what will happen, this K p and 1 by K p, actually that part should be, we can say this one, for maximum adsorption to happen, we can say 1 plus K p, that will be much greater than, say that will be, we can say this 1 plus K p will be almost equal to, we can say 1 plus K p will be almost equal to this one, that is almost equal to K p, or we can say K p will be very high. So, then in that case Q will be Q m is nothing but this, we can say whatever the value actually we got, this one Q will be equal to, for this case like 6.4 p divided by say 1 plus 1.53 p will be converting into 1 plus 1.53 p, means say this denominator will be converting into K p, because this also K p is much more higher than this one, that is why this will be like Q will be equal to Q m. Okay. So, in that case what will happen, this that will be equal to 6.4 by 1.53, that is coming out as 4.183. So, that is we can say millimole per gram. So, okay. Now, we see we are trying to get this one in terms of gram per gram or kg per kg. So, we will be just multiplying with molecular weight. So, that will be 4.183 into molecular weight is 65. So, and millimolar, that is this one, say gram per gram or kg per kg, whatever may be. So, that will be 0.272. So, kg adsorbent per kg adsorbent. Okay. So, that is we can say kg adsorbed per kg adsorbent. So, we can say the Qm or maximum amount will be adsorbed, like if we use 1 kg active charcoal, then 0.272 kg this one what is called this gas will be entrapped here. Okay. So, now we have another problem like this, we can say the equilibrium adsorption data for the propane on activated carbon at two different temperatures are given in the next slide. This we need to fit the data using this Langmuir isotherm and get the correlation coefficients like Q m and K, and also we need to determine the isosteric heat of adsorption values. Okay. So, here actually we have these two temperatures. We have this first temperature is 310.1 Kelvin and the second temperature is 366.5 kilo Kelvin. Okay. So, the pressures are given as suppose 2.27 kilopascal pressure, then Q will be 1.044, like that way. If we increase the pressure, so then we can say Q also will be going on increasing. For 310, so suppose this is one trend, if we use this higher temperature, then say we will be getting like this this we can say we will be getting more Q values actually with various pressures. Like this, if we increase this pressure from 21.07 to 634.3 kilopascal, that 366.5 Kelvin temperature, then the this one millimole adsorbed per gram adsorbent will be increasing from 1.677 to 4.1. we can say 4.244 millimole per gram. Now, we need to find this we can say this K value, QF value and isosteric heat of adsorption or delta H. We need to find out this, we need to find out 3 values. So, firstly we will be plotting this, as we have this P and Q values. Suppose P and Q values, then we will be doing P by Q like this. If we do P by Q for all these cases, we will be getting P values for 310.9 Kelvin and for 366.5 Kelvin. Then we will be plotting this one, then we will be getting the straight line like this. Okay. Now, we will be getting this. So, suppose this line is for 310.9 Kelvin, this is for 310.9 Kelvin, this is 366.5 Kelvin. Okay. Now, from here actually we will be getting, say, we know this for Langmuir isotherm S is equal to 1 by q m and slope and intercept is equal to 1 by q m into k. And if we do this slope by intercept, for this case we will be getting this k value. From only slope value we will be getting 1 by q m, and if we know this intercept value for 310 and this is for 366. So, this is say for intercept for 310.9 Kelvin, this is intercept for 366.5 Kelvin. So, that will be the intercept for this one, and the slope will be for 300 and this slope will be for 366.5 Kelvin. Now, we will be getting this one say at 310.9 Kelvin, we can say slope, whatever slope actually we have this, if we do this 1 by slope, then we will be getting 1 by slope is equal to say q m, that is obtained from this curve actually, that is 4.695 so millimole per gram. And this intercept also we need to find out, whatever the intercept is here, from there we will be getting the slope by intercept, there k is equal to, we can say this one using this we can say this whatever q m we have this one like 1 by slope, and from there we will be getting 0.096 kilopascal inverse. Similarly, for we can say for 366.5 Kelvin, we have this q m is equal to say 3.802 millimole per gram, and this k value will be like the from the slope and intercept, slope by intercept we will be getting 0.0374 kilopascal inverse. So, now we have this one for 2 temperatures, we have this this we can say q m. So, for 310.9 Kelvin we have this q m is equal to 4.965 and k is equal to 0.096. For 366.5 Kelvin 3.802 and k value as 0.0374. Okay. Now, we need to plot this, we can say we have to get the isosteric heat of adsorption values. Okay. So, for that what we can do, let us take any q value like this, let us take say q is equal to 4 millimole per gram. Then say we will be plotting this suppose ln p and say 1 by t, because we this one we have this formula like this delta H, this isosteric heat of adsorption value is equal to minus R T square into d ln p by dt, or we can say this one 1 by d ln p by d 1 by t. So, that is why if we plot this 1 by t and ln p, then for different ln p versus values at 1 by t value, we will be getting say for 310 and 0.9 and 366.5 Kelvin temperature. If we plot this one, suppose we will be getting for say this one, suppose one point will be here, say 1 for 1 by, say we can say 1 by 366.5, and suppose another value will be 1 by 310.9 Kelvin. So, in that case whatever LNP value actually we will have, this one will be adding these two. Okay. The slope actually will be is equal to, say that value we have this slope. So, from the data point whatever we have this one, if we say q is equal to 4 millimole per gram, if we plot they put this one, then slope will be minus 4745.46. Okay. So, then we can say the from the slope we can say we will be getting this one, so delta H will be that is slope. So, is equal to we can say delta H isosteric will be equal to say minus 4745.46 into 1.987. So, it will be kilocalorie per say gram mole. That will be coming out as 9.429 kilocalorie per gram mole. Okay. So, we can say this one delta H isosteric is equal to minus 9.429 kilocalorie per gram mole. Okay. So, that is we can say that amount of you can say enthalpy will be generated during this adsorption process. Okay. So, that is plotted here, and now we will be discussing about the classification of the adsorption systems. So, there are three different adsorption systems are there, like this single transition system is there, then two transition system is there, then multiple transition system is there. Okay. So, in single transition systems, this one adsorbable component plus inert carrier, like this we can say maybe isothermal or near isothermal operation will be there. In another case is for single transition system, two adsorbable components are there, there is no carrier, maybe isothermal or near isothermal systems. For two transition systems where the two different transitions will be there, two adsorbable components plus inert carrier, maybe isothermal operation. There may be say three adsorbable components without any carrier, maybe isothermal operation, and third type will be like this, one adsorbable component plus one inert carrier, maybe adiabatic operation, and these two adsorbable components without any carrier and adiabatic operation. So, these are we can say this one for two transition systems. For multiple transition systems we have 4 or more components and operation will be isothermal. Then second type is 3 or more components, then adiabatic operation. Third type is that 3 components, isothermal operation with selectively reversal, and fourth one is 2 components, then adiabatic operation with selectively reversal. So, there are we can say this one, these 4 types of multiple transition systems. Now, we will be discussing about the dynamics of the adsorption column for single transition system and multiple transition systems. We will be discussing briefly. Let us take this is the adsorption column, and say the differential thickness is dz and z is increasing from the bottom to top, with the velocity of the we can say this gas adsorbent is v. Okay. So, the differential mass balance equations for an element of the adsorption column and for an adsorbent particle within such an this one element provide the starting point for the development of mathematical model to describe the dynamic behavior of the system. Okay. The fluid stream containing concentration of the C like this, whatever the fluid stream is there, the concentration of the C is the function of Z and T, because the concentration will go on changing from the bottom to the top of this column and with time also. And axial dispersed plug flow, actually we are assuming this one, this whatever the flow is, this is axially dispersed. Okay. So, the differential fluid phase balance will be like this, minus dl into del square C by del Z square plus del Z of say V into C plus del C del T plus 1 minus epsilon by epsilon into dq by T is equal to 0, where this q is equal to, we can say, volumetric flow rate of the we can say adsorbent. And say we can see this mass balance for adsorbent particle, else the adsorption rate expression of this dq by del q by del T, that is the function of q and C. If the system contains two adsorbable components rather than one adsorbable component, so in an inert carrier like this, the mass balance equation may be written for both the species like this. So, we can say this one I and J. So, we can say this in terms of I and J, we will be writing these equations. And for equilibrium consideration of the system, we can say three general cases can be distinguished depending on whether the equilibrium relationship is either linear, favorable or unfavorable over the concentration range corresponding to the transition considered. So, in case of this single phase transition like this, so we can say it may be, say, the linear, may be favorable or may be unfavorable. So, the XY diagram actually is simply a non-dimensional representation of the equilibrium relationship expressed in terms of the reduced variables like this, say q star minus q o prime by q o minus q o prime, and the in terms of, we can see this concentration, that is C minus C o prime by C o minus C o prime, where we can say this the quantity q o minus q o prime represents the respective charge changes in adsorbed phase, wherever the C o minus C o prime represents the respective changes in the fluid phase concentrations over the mass transfer zone. So, where the mass transfer zone is there, we will be discussing about the details of the mass transfer zone MTZ in detail. So, in the next class actually we will be discussing this one. But you see this one, whenever the three general cases are there, whenever we will be saying that this is a favorable case, or we can say this one the adsorption process is favorable, or we can say this is the realistic one, then we can say the increase in the C minus C o prime by C o minus C o prime, that will be very less compared to this q star minus q o prime by q o minus q o prime. Okay. So, that is why we can say this q star minus q o prime by q o minus q o prime will be greater than C minus C o prime by C o minus C 1 prime. So, that is why we can say whenever this quantity y quantity is increasing very fastly, but you see this x quantity is increasing very slowly. So, that is we can say this adsorption process is favorable. So, that is why it is, we can say this is the favorable condition. But whenever these two quantities are same, or we can say this one whenever it is a diagonal one, then we can say this one for linear one, we can say this one it is linearly dependent. So, we cannot say it is very favorable or it is not favorable or unfavorable, but it is follows the linear relationship. But whenever we say this one unfavorable condition, so whenever we can say this one the y component is increasing very slowly, then x component like this, say this we can see that type of condition where we can say C minus C o prime by C o by C o prime is increasing very rapidly, where we can see this one whatever the q star minus q o prime by q o minus q o prime is increasing very slowly. So, that is we can say this one unfavorable condition. So, these are the three different cases we have. Now, we can say this one we will be doing the classification of single transition systems like this, depending on the nature of the equilibrium relationships, it may be following this linear isotherm, maybe we can say favorable isotherm, we can say unfavorable isotherm also. Depending on the isothermal or near isothermal condition, we can say the single transition systems may be classified into maybe isothermal or near isothermal. So, depending on the concentration level of the adsorbable components, it may be trace system or may be non-trace system. Whenever we can say this one, depending on the flow model, whatever flow is actually taking place in the single transition system, we can say it may be plug flow, it may be dispersed plug flow. So, both types may be there. Then in terms of the complexity of the kinetic model, we have these 4 different types like negligible mass transfer resistance, then we can say single mass transfer resistance, 2 mass transfer resistances, and then 3 mass transfer resistances. So, these all 4 different types of complex kinetic models are present. Now, we will be discussing about the multiple transition system. Whatever the transition systems are adopted for single transition systems, for multiple transition systems only will be this one writing all the expression in terms of ith term. Like this, if we consider an element of the bed through which a system containing a concentration of Ci, so of adsorbable species I is flowing. So, we can say other species also are there. So, then we can say the differential fluid phase balance equation for each component will be. So, whatever we have written actually in the for the single transition systems like this, only the difference is like this in the concentration terms, or we can say this one in the we can say this loading term, or we can say this one capacity terms, minus dl into del square Ci by del z square plus del z of V into Ci plus del Ci by del t plus 1 minus epsilon by epsilon into del Qi by del t is equal to 0. Then particle mass balance yields the adsorption rate equation for each cases like del Qi by del t, the function of suppose Qi, then Qj, Q, then up to Qn and Ci, Cj and up to we can see this one Cn. Okay. So, this is we can the function of all these we can say Q terms and as well as this concentration terms of the individual components. Okay. And now will be this one we have this adsorption equipments like this, we can say the widely used this packed adsorption bed like this, it is the batch process. Suppose the we can say this one adsorbent bed actually is placed here in between say suppose two we can say this one supports, perforated supports, and say this there some support balls also are present just below the support like this perforated support, and then the entire part actually is filled with the support balls. And say suppose the through this distributor, suppose this adsorbate will be entering adsorbate, and suppose adsorbent is filled here, and whenever it will be coming out exhaust free of adsorbate. Okay. So, this exhaust actually will be there, that is of free of adsorbate, or we can say this one target component will be here only with this. So, now once the process will be over, then it will be like adsorbent plus adsorbate. Okay. Whenever we will be talking about the continuous moving bed like Higgins apparatus also, suppose the we can say suppose this adsorbent carrier gas actually is entering from here, and this we can say we have this we can say this one inside this one we can say suppose this this will be the say adsorption section, and this will be desorption section, or we can say regeneration section, and then clean gas means say this one adds the exhaust gas free of the adsorbent actually will be coming out from the top of this one. And then we can say this one whatever the we can say desorption solute this component target component desorption solute actually is used, that is actually again regenerated, and we can say whatever the we can say this one adsorbate will be there, that is again we can say this one reused using the other mass transfer operation. Then so we can say now we will say thank you. So, in the next class we will be discussing on the steady state fixed bed adsorbers and the last topic as ion exchange.